Behind almost every scientific study we read about, there's this quiet little assumption, a kind of golden rule for statistics. It's what helps researchers make sense of all their data. But what if that rule isn't just a little off, but fundamentally flawed? Well, that's the surprising controversy we're digging into today. It's a paradox that sits right at the heart of how science gets done. So at the center of all this is something called the normal distribution. You probably know it as the bell curve. Just think of it like a perfect recipe for data. In this ideal world, everything is neat and tidy, clustering perfectly around the average. And hey, this assumption is super convenient because it lets scientists use all sorts of powerful, easy-to-use statistical tools.
But that's where we hit a snag, and it's a big one. The real world, it's messy. Data is almost never that perfect. So what happens when you try to use a recipe designed for a perfect world on the chaotic, unpredictable data you actually get from real life?
Right, so let's start by really unpacking this so-called golden rule of statistics and find out what happens when reality just refuses to play along. This is especially true when you're studying people. In fields like psychology or education, human behavior just doesn't fit into a neat bell curve. I mean, think about something like personal income. It's not a symmetrical bell shape, right? It's heavily skewed with a long tail of super high earners. And this creates a huge problem. If your data doesn't fit the recipe, can you actually trust the results you get from tests that were designed for it? So imagine you're a researcher. What are you supposed to do? The advice you get is, well, it's a total mess. You've got some textbooks telling you absolutely have to test for normality. Then you've got other experts saying, nah, if your sample is big enough, don't even worry about it. Meanwhile, the American Psychological Association is like, hey, just tell us what you did. And to top it all off, some scholars argue that the very act of testing for this stuff can actually introduce brand new errors. It's a complete statistical minefield. And this confusing mess of advice leads us straight into what the source material for this explainer calls the normality paradox. It's a really frustrating statistical catch-22.
Okay, here's the paradox in a nutshell. When you have a small amount of data, a little hiccup, a deviation from that perfect bell curve can completely throw off your results. This is when you really need to go to alarm system. But guess what? The tests for normality are too weak to even notice the problem. Now let's flip it. Say you have a huge data set. Your main statistical tests are now robust enough to handle little imperfections. But now, those normality tests become way too sensitive. They'll start blaring the alarm for tiny, completely harmless deviations, causing a panic for basically no reason.
The paper we're looking at really nails it with this quote. It says, these formal tests have low power when you need them most with small samples, and they're too sensitive when the problems don't really matter with large samples. It's kind of like having a smoke detector that can't smell a real fire but goes off every time you make toast. It's just not the right tool for the job. So, is there a way out of this paradox? The study we're covering basically went on a mission to find out, to figure out how to choose the right tool for the right job. What these researchers did was pretty epic. They ran what was basically a massive statistical stress test. First, they created 18 different flavors of messy, non-normal data, the kind of stuff you'd actually see in the real world. Then, they took 18 different normality tests and threw them at each type of mess to see which ones could actually spot the problem. And they didn't do this just once. Oh no. They repeated this whole thing 10,000 times for every possible sample size to see which test came out on top. So, after putting all those tests through the ringer, what did they actually find? Well, it turns out the verdict from all that data was surprisingly clear. Okay, let's look at the evidence. Check out this chart. It's showing us how good different tests are at spotting a specific problem, skewed or kind of lopsided data. So along the bottom, you've got the sample size, how much data you're working with. And up the side, that's the power of the test, which is just a fancy way of saying how good it is at finding the problem. Now, you don't have to be a statistician to see what's going on here, right? Some of those lines, look at the ones at the very top. They just shoot up. They get really powerful really fast. Those are our superstars. But then look down at the bottom. See that sad little line struggling to get off the ground? Yeah, not so great. It's clear that for this specific kind of messy data, some tests are just way, way better than others. And what's cool is the study boils all of this down into a handy little cheat sheet for researchers. And the big takeaway is this. There is no single best test. It all depends on how your data is messy. If it's lopsided or skewed, you need one set of tools. But if it's symmetrical but has, say, weirdly high or low peaks, what statisticians call kurtosis, then you need a completely different toolkit. It's all about matching the right tool to the specific problem you have.
Okay, so we've been deep in the statistical weeds here. Why does any of this technical stuff actually matter? Well, let's zoom out and connect this back to the bigger picture, way beyond the lab.
So what's the bottom line here? First, like we just saw, there's no magic one-size-fits-all test. Second, and this is a huge one, the popular default choice often isn't the right choice. The study found that one of the most common tests out there is only popular because it's the default option in a software package, even though it's a terrible performer. I mean, just think about how many studies could be using a faulty tool just because it's the easy button. It really proves that context is everything. Good science means thinking carefully and choosing the right tool, not just clicking default. So, the next time you see a headline about some big new scientific finding, I want you to remember the iceberg. That headline, that big result you see, that's just the tip. Underneath the surface, there are dozens of these small technical decisions that researchers have to make, like which statistical tool to use. And as we've just seen, making the wrong choice on one of those hidden steps, well, that can change everything.